What's up guys, welcome back to a brand new video. This video, linking to the previous one, is about supersymmetry and my pen has too much ink. So while I make this smaller, hit that like button and subscribe. So anyway, we're learning about I'm just gonna write it like this now. No, that doesn't work either. Supersymmetry. I'm gonna take 10 years to write it. And I have to put it in 10 lines. Okay, messy supersymmetry. So what is supersymmetry? To understand supersymmetry, we have to understand that there are two classes of particles called bosons and fermions. So since we're not going to use much time, I'm just going to represent this one by B and F. Okay, so the main difference is that bosons have an integer spin like 0, 1, or 2, or also known as whole numbers. I don't know particles that have spin 3 or 4. And then on this other hand, we have particles that don't have an integer spin, such as half. And I'm not sure if this exists, but I don't know, 1.5 if it exists. But I know there are half spin particles like electrons. 0 spin is for, like, I think a gluon, photon, Z boson, or a weak boson. One spin is for, one spin is for a gluon, photon, Z boson, or a weak boson, and the 0 spin is for like a Higgs boson. The 2 spin is for the hypothetical graviton, or also known as a tensor boson. So supersymmetry aims to fill these gaps. There are certain gaps that come between them that are like unsolved. So let me just represent it by this messy drawing. So these gaps need to be removed. That's why supersymmetry is there. Supersymmetry aims to remove these gaps by making each particle have something known as a superpartner. The superpartner of a particle will have half more or half less spin than its original particle, therefore making a boson always a boson superpartner a fermion, and a fermion superpartner a boson. And according to the math that goes with it, it cancels out a bunch of problems that appear when differentiating between bosons and fermions. So, what does supersymmetry have to do with string theory? But before we go to that, let me just mention that the superpartner of a particle is, according to the math, always heavier than the particle itself, which is why superparticles are a candidate for dark matter. So anyway, now we're going to see what supersymmetry has to do with string theory. Let's just remove this all. Maybe we will not have to draw anything at all. So obviously the first string theory, bosonic string theory, required boson. I'm just gonna call it B string theory in the video because I mean I'm not gonna be able to write like that. B string. BS. I'm getting very lazy with my writing because I'm having a hard time writing with a trackpad. So BS. On the other hand, we have superstring theory, which is SS, and well, then that became into M theory, which is MT, I guess. So this required 26 dimensions, which was not okay. So these only concerned bosons, so they added in fermions along with supersymmetry and maybe supergravity, which is the idea that a graviton also has a particle that is its superpartner. Now when they did this caused superstring theory, reduced 16 dimensions and turned it into a 10-dimensional theory, with problems which increased to 11-dimensional theory, and that was supergravity's good number as well, which is why M theory is the current candidate for string theory and a theory of everything. So I guess that wraps up today's video, guys. Thank you guys so much for watching. If you guys enjoyed, smash that like button and subscribe and turn on that post notification bell so you don't miss videos and you're the first to watch them. Anyway, thank you guys so much for watching, and I'll see you guys in the next video. Peace.